Good morning, everybody. Start with some green check marks. And any questions you might have had from the material from last day. I want to review some stuff. I found a few extra questions on half-life and decay type equations that I want to go through today as well. So we're going to do that. And just a little brief review of Unit 7. And then that'll be it for Unit 7. So hopefully you guys have a few questions, but if not, that's always a good thing. If you don't, I'm just going to jump into the material. So is it okay if we estimate some of the answers for those questions? Yeah, that's fine. Like I was saying last day, generally speaking, the questions you guys get will be full half-life type questions. You won't have to deal with like parts of half-lives, like the first question, I think it was number 11 on the learning guide. I did find a formula that you guys can use, but I hesitate to give it to you because you just have to memorize it, and it's kind of difficult to use and stuff. So I'll show it to you, and if you want to use it, then you can go ahead and do that. But if you don't, then that's fine as well. I can go over that one, Haley, for sure. And maybe we'll just start with that. And then if anybody has any other questions, they can chime in. Number 5, what was that? Number 5, page 7. Determine the number of neutrons necessary to complete the fission equation. Okay, so we'll look at a few extra examples of this type of question today in class, but essentially what we need to do is make sure the math works out on both sides of the equation. So again, we need to kind of think about the arrow as being an equal sign. So I'm just going to maybe put a little equal sign above it just to kind of remind us of that. And then what I'm going to do is just do the math. So on the top here I have 235 and 1 together gives me 236. And then on the bottom I have 92 and 0 is 92. 57 and 35 gives me 92, so that works out because I know I have 0 here. And then on the top I have 145 and 88. What's that going to give me? 145 and 88. 243? No, 233 maybe. 145 and 88, 233. So these two together give me 233. Now, on the reactance side, I had 236. Now I only have 233. So the bottoms worked out, 92 and 92, those are equal on both sides. But on the top, I'm starting with 236 and I'm ending with 233. So I need an extra 3 of these neutrons, but I can't change this 1 to a 3 because that's not a neutron anymore. That's just 3 neutrons joined together. So all I can do is add a coefficient in front. So if I put a 3 in here, I'm going to have 233 plus another 3 is equal to 236. Now I have 236 and 236, 92 and 92. So the top number matches the bottom number in terms of equal on both sides. So that's kind of how that one's done. A lot of them are really quite similar to that. It's always just looking at the math on both sides of the equation and going from there. A couple more questions came up here. What do we have? Number 5. I'm still having troubles with 6, number 12. All right, let's do that. And then 11 and 13. Page 6, number 12. All right, the half-life of the isotope sulfur is 87 days. The initial sample contains 300 grams. What mass would be left after 1 year? You need to calculate the number of half-lives passed to one decimal place and use the graph on page 2. All right, so we didn't have a chance to find that graph, or I didn't know where it was, but let's do this. If I had 1 year, that's 365 days. That's 1 year. And it says a half-life is 87 days. So I'm going to see how many times 87 goes into 365. So if I take 365 divided by 87, that is 4.19, let's just call it 4.2 half-lives. So that means our sample is going to go through 4.2 half-lives. All right, and now it says to go to the chart on page 2, but if I go up to page 2, there is no chart there that I can see. Following elements, isotopes, so nothing to do with sulfur there, so that doesn't really help us at all. If we had a chart that compared the number of half-lives as a percentage, we could look at that. If we had something like this that had half-lives down on the bottom and then percentage on this, and we had 100 and 50 and 25 and 12.5, and our decay curve went down like that, we could look at it. We can say, okay, there's 1 half-life, there's 2 half-lives, there's 3 half-lives, there's 4 half-lives, there's 5 half-lives. And what we could do is say, okay, here's 4, here's 4.2 right here. I go up and then I go across, and then I see what I have in terms of a percentage, and then I could go from there. We don't have that in this situation. I guess the chart is gone, or I don't know what this learning guide's referring to with respect to that question. So I said I would look at maybe a formula you guys could use, and we'll see if we can make it work, because we don't have that chart. So Taylor, to answer your question, normally you'd have a chart, but this case we don't have a chart. And it gives us a goofy, uneven number of half-lives, which is kind of unusual. So let's use this formula. Y is a 1/2 to the x. Thinking, wow, that's kind of confusing. So y is the amount that's left. A is how much you started with. So we're starting with 300 grams. And then I have 1/2. And then x is the number of half-lives that we've gone through. And this will work for the question up above as well. So what we're really saying is, if I'm going to divide by half 4 times, or 4.2 times, and I'm starting with 300, then how much stuff am I going to have left over? So this is kind of getting to what you're saying there, Abby, that I understand, but the decimal thing is confusing. And generally speaking, on the provincial exam, on tests and things like that, you won't end up with decimals for half-lives. It's going to give you a whole number of half-lives. Or at the very most difficult question would give you perhaps a half of a half-life. But it's just kind of beyond what you're expected to know in grade 10. So I'm not exactly sure why it's here, but it is. So let's just continue on with it. So in my calculator, I'm going to go 0.5, and then I'm going to use the exponent, 4.2, and then I'm going to multiply it all by 300, and I'm going to see what I end up with. So 0.5 to the power of 4.2, and then I'm going to multiply it by 300. And I end up with 16.3 grams. All right, so there you go, 16.3. Does that make any sense? Well, let's figure it out in terms of our table, because I love using these tables. So we have half-lives, we have time, and we have the amount. So half-life 0, 0 time has passed. We're starting with 300 grams. After 1 half-life, we're at 87 days, and we're down to 150. After 2 half-lives, what's that, 43.5 No, I'm doubling it. 174 days, 75. This math is getting too big for my head. 174 plus 88, 260, so 260 days. 75 divided by 2 again is 37.5. 4 half-lives is going to be 347 days, and then 37.5 divided by 2 again, 18.75. All right, so we're at 4 half-lives right here, and we have 18.75 grams left. Now the question is asking not 4 half-lives, but 4.2. So we should be close to that 18. The 16.3 that we got using that formula actually kind of works, so I'm thinking we did it right. How would I do this on a test? A lot of you are probably thinking, well, you'd have a chart to look at. So we're not going to give you a fractional half-life question without a chart or something along those lines. So I don't know where the chart is that this question is referring to, and that's why things are a little bit difficult here. Needless to say, 16.3 is the answer you're hoping for there. So can you use the equation on the exam? For sure. You can use it, but you got to memorize it. And I don't know if it's worth memorizing. That's why I hesitated to kind of show it to you in the first place. But if you know how to use it, you want to use it, it'll do all your half-life questions for you. So just kind of a good way to find the answers to the questions if you wanted to use a formula. There were a few other questions in chat. Number 6, page 12, 11 to 13 on page 6. Page 6, number 11. All right. The half-life isotope, 15 hours, 3 days, 12 hours. So 3 days, 12 hours is 84 hours. We're going to take 84 and divide it by 15 to figure out the number of half-life. So it says we're checking on this thing after 3 days and 12 hours, which is 84 hours in total. And the half-life's 15 hours. So if I take 84 and divide it by 15, I get 5.6 half-lives. All right, let's continue on. 5.6 half-lives. Let's use our formula again that I just wrote down. Y is a 1/2 to the x. So I'm going to put this 5.6 in for x. I'm starting with 1,000 grams. 1/2 to the power of 5.6. So on my calculator, I go 0.5 to the exponent 5.6, hit my equals button, then I multiply by 1,000, and I end up with 20.6 grams. Is the amount left over. So we started with a table. It was 5.6 half-life, so we were kind of midway between the 5 and 6 point. If you're on a test and you don't remember the formula, but you're midway between 5 and 6 and you can pick the closest answer, I mean, that would probably be your best bet on a question like that. So there you go. Hopefully that helps. 11 and 13. Fossils analyzed, determine the percentage of original carbon-14 remaining is 25%. How old is the fossil? So this is the table. that we're going to use for most of these questions: half-life, time, and percentage. There you go, that one's done. And then number 7 on page 7. What is this simple 4-letter word for an uncontrolled chain reaction? Releases a lot of energy. Simple 4-letter word for an uncontrolled reaction. I'm drawing a blank here. Bomb? Sure. I was thinking like boom. But bomb makes sense. If we have an uncontrolled chain reaction that releases a lot of energy, that's an explosion, but that's more than 4 letters. So I'm not really sure what that question is getting at. But if you get to the end and had to look it up, then that's fine. I guess the question is trying to get the idea that if you have a controlled chain reaction, that's what we use to generate electricity, power. An uncontrolled chain reaction will lead to an explosion. It probably is in reference to something in the notes, but I can't be sure. What order do you multiply the equations so the half is first and the exponent? Since we already did that much once. Okay. Taylor, with the equation, I kind of work my way backwards. So in my calculator, I would write, I'll write up here. I would write 1/2 is the same thing as 0.5. So I would go 0.5 on my calculator, and then I would go, on my calculator, it's y to the x. And then I would put in 5.6, and then I would hit equals, and then I would multiply it by 1,000, and then hit equals again, and you should end up with 20.6. So kind of working your way backwards. All right, that's hopefully good. We'll look at a few more. I think it's because the concept of bombs came from uncontrolled chain reactions. Yeah, it's in the notes. All right, perfect. It is what it is. On page 4, didn't understand what 1 and 4 asking. Okay, let's just look at it real quick, and then we will... Page 4, number 1. There are 2 types of isotopes that we can compare to each other in order to determine the age of a fossil or other material that used to be alive. What are they, and what is the half-life of the radioactive isotope? So living things have carbon in them. So if it's asking about something was living, like a fossil, it's talking about carbon. So carbon, wasn't a very good C. Carbon-14 decays into nitrogen-14, and it takes 5,730 years. So that's kind of important. You can't use carbon dating in like a rock or something because rocks don't have a lot of carbon in them, and rocks are generally very old, so you're going to have to use something like uranium or something with a longer half-life. There are 2 isotopes that we can compare each other to determine the age of rocks. What are they, and what is the half-life? So again, uranium. Find my data booklet here. On the back page of the data booklet, the very last page, you have the little chart at the top of the page, and it has all of the half-lives, parent-daughter pairs, and then the amount of time it takes them. So just using that essentially is what you're doing there. Okie dokie. Let's jump into this first. So in the course, at the bottom of Unit 7, I have added a sheet, and we're actually going to go through together today, so you don't even really need to download it, but here it is. Half-life decay equations, extra practice. I have a booklet with a bunch of sort of worksheets in it, and I included it because we didn't have a ton of these types of questions. So we're going to look at those in class in a second. what I want to do first is talk a little bit about what we've been looking at. Unit 7 review. So last day I wanted to watch this video, but we didn't really have enough time, and it's 15 minutes long, so we won't watch the whole thing, but just give you an idea of sort of the amount of nuclear bombs that have been detonated on Earth. So the video shows all of the nuclear detonations that we know about, all of the kind of declassified ones from all over the world for the last, well, since 1945, when the first nuclear weapon was detonated. So I always think it's fun to have students guess how many nuclear bombs have been detonated on Earth between 1945 and 1998. So between the 40s and the 90s. So we're talking like 50-year span. Is there one over the ocean? Yeah, there's lots that are tested in the ocean and lots that are tested on some small islands in the Pacific. And we'll talk a little bit about why that is in a second. So in chat, just guess how many nuclear bombs have been detonated. We've talked about, we know of 3 for sure, or 4 I should say, because they did their first test bomb in New Mexico. They dropped 2 during the Second World War to end the war. And then we talked about the Tsar bomb that the Russians detonated. So there's 4 for sure from the United States and the Soviet Union. So there's 2 countries involved. Guesses. What are we thinking? Hundreds? 70? Near 100? Yeah, and this is taking into account both fission bombs and fusion bombs. So we're talking both types of bombs here. Goes back to P, S, and L waves in the plate tectonics. We can't use them to detect radioactivity, no, but we can use them to determine when bombs have gone off. The seismic waves that are created, for sure. All right, so we've got guesses in the 70s to about 250. That's a big number, Haley. In terms of dropping a bomb in the ocean, in the middle of the ocean, Ava, is that what you're referring to there? The idea is, yeah, essentially that you end up with radiation. So this is why they stopped testing bombs above ground and stopped testing bombs in the ocean. So it starts off kind of slow and it's kind of hard to figure out what's going on, but we'll do our best. So you'll see each flash represents a bomb detonation. The first one was in New Mexico. So this was the Trinity test. And up at the top, you can see the year and the month. So 1945, the 7th month, is that August, I guess? And then that same month, a month later, a few weeks later, I should say, the first bomb was dropped on Hiroshima, so this is in Japan. And then a few days later, another bomb was dropped in Nagasaki, Japan. So the first 3 bomb detonations happened within a few weeks of one another. They established that they could make the bomb go off, and then they dropped 2. The first one was a uranium-235 bomb, and the second one was actually a plutonium bomb. Once they enriched enough plutonium, they tried that to see if they could do it, and it worked. And then that, of course, ended the Second World War. And then you can see it's kind of quiet for a bit. Bottom right-hand corner, you get a little running total, and the flags of various countries appear. So another kind of year went by, and then they started testing more bombs, but they realized the radiation and the materials that were created were really dangerous, so they started testing in the middle of the Pacific on some islands called the Bikini Atoll and some other ones. So we're at 5 right now. This is 1948. And they keep testing them in the middle of the ocean so people don't get hit with fallout, things like that. 1949, A year later, you can see the Soviet flag appears, and they detonate their first bomb a year after the United States. And then time goes on, and then something happens in a little while here. We'll see. You can see a few more bombs detonated in the New Mexico area. The United States is up to 17. Soviets are up to 3. So 1952, we're up to 35 bombs. Then the Great Britain develops the bomb, or the United Kingdom. And because if you think about where the United Kingdom is, this little island here, there's not enough room on this island to detonate a bomb. So they start detonating them in Australia, which is part of the British colony. And there's lots of space. So they detonate them in the middle of the outback. And you can see the Soviets, bunch of testing going on. And the United States gets a little bit crazy. Soviets trying to catch up. I'm just going to fast forward a little bit. You can see a few more countries have come on the scene now. So France develops a bomb. And of course, France is a densely populated country in Europe. So they test their bombs in Africa, which was a French colony at the time. I forget what country exactly. So you can see things start to get a little bit crazy here. The late 60s, early 70s. Does anyone know what significant period this was in the Earth? What we called this arms buildup? There are bombs that we detonated that we don't know about. Yeah, it's completely possible. So 1964, China detonates their first bomb. So these are the ones we know of. It's possible that ones exist, but there's really no reason to keep them secret at this point. So this is the 60s, late 60s. This is the start of something called the Cold War. And the Cold War was basically an arms race to see who could build the most bombs. And there was one principle that kept us kind of safe during the Cold War, and it was called MAD, which is an acronym, M-A-D. And it was called Mutually Assured Destruction. So the idea was this: if the Soviets launched a nuclear warhead at the United States, it would take some time to get from Russia to the United States, and vice versa. If the United States launched one at the Soviets, it would take a few hours to get to Russia. So as soon as one country detected the other country's launch of a nuclear missile, or an intercontinental ballistic missile, an ICBM, they would be able to launch a counterattack before the first bomb had even gone off. So this was kind of the only thing that stopped World War III from happening at this point, was because these countries knew that if they launched an attack at one another, they would receive attack upon themselves. And you can see that the grand total's up to like 1,180, 90. They just kept testing them. You can jump ahead a little bit further. India is on the scene now. I forget what year their first bomb was detonated in, but they became a nuclear power. And we're up to 1800. Yeah, the world almost ended because of the Cold War. For sure it did, many, many times. There is something called the Cuban Missile Crisis. There's a really, really good movie about it. It's kind of like a Hollywood's portrayal of it. It's called 13 Days. If you've never seen it before, I recommend watching it. It's pretty crazy how close we came to nuclear war. The Russians were sending missiles to Cuba because they could strike the United States without, receiving a retaliation immediately, sort of thing. It was only, I think there's like 80 miles between Cuba and the United States, and they turn their ships around at the last minute. The United States detonates them in the middle of the Pacific Ocean. They have some islands there. as well as the United Kingdom and France, all these densely populated areas. Have we, as Canadians, developed a nuclear weapon? No, we have not. We have our neighbors to the south to protect us, and we're really not into that sort of thing in Canada. You know, good peace-loving Canadians. So this is 93. We're at about 2,000 bombs. And in 1998, when this stops, things kind of slow down because technology was getting to a point where we could test these bombs in computers, and there was a disarmament. So the United States and the Soviets decided to get rid of some of their bombs. So that was Pakistan. They detonated a few, and then India detonated 4. So this is just kind of going through each country. China detonated 45 in total. We use CANDU reactors to generate electricity for sure. So this is the French. The French have islands in the Pacific, and they have colony in Africa. So that was 210 that the French detonated. You can see Great Britain detonated some in the United States. They detonated some in the Pacific and detonated some in Australia. So obviously the United States and Great Britain were in cooperation there. 715 for the Soviets. There's all 715 of them. So the size of the circles just represents like frequency. This is the United States. This is 1,032 nuclear bombs that they've detonated all over the place. Mainly in the Pacific, lots in New Mexico. So there you go. I always find it interesting how students, because you guys grew up in a time where you didn't really have to think about nuclear weapons at all, your number of bomb detonation guesses are often really, really way off. And obviously, since then, more bombs have been detonated, but not very many. And the one extra country that's on the list now is North Korea, which has nuclear capabilities as well. So they've detonated less than 10, I'm pretty sure. So there you go. Yeah, so the United States detonated about 1,000. Soviets were about 715. Pretty scary stuff. But anyways, there you go. So there's some islands in the middle of the Pacific that are highly radioactive. A lot of bombs were detonated below ground in the last few years to protect from radiation fallout. We talked a little bit about radiation and how much you can receive in terms of just everyday things. So the unit we're talking about here is called a sievert or a microsievert. It's a level of radiation exposure. So if you were to eat a banana, you'd receive about 0.1 microsieverts of radiation. A CRT monitor is a cathode ray tube. If you're using it for a year, you'd get about 1 microsievert. If you got an X-ray at your dentist, you're looking at about 5. And then the extra dose one day on average near Fukushima, where the reactor meltdown happened there in Fukushima in Japan, is about 3.5. All right, so those are kind of everyday sort of exposures. If you flew from New York to LA, you'd receive about 40 microsieverts. So as soon as you get a little bit higher up in a plane, going above the atmosphere absorbs less radiation from the sun, and you get exposed to more radiation. So if you're an astronaut at the International Space Station, you're receiving a lot of radiation because there's no atmosphere to protect you up there. So that's kind of one of these concerns we have about space travel between stars and going to Mars and things like that. You get exposed to a lot of radiation. All right. One day at a site 50 kilometers north of the Fukushima disaster was 3,600 microsieverts. We all experience about 2,000 microsieverts a year. So that's kind of the standard. If you get one mammogram, that's about 3,000. People make a big deal about microwaves. Are they a threat? Microwaves, you'll remember on the scale of, we looked at the electromagnetic spectrum. Microwaves have very low energy and they have very long wavelength. The microwave wavelengths in the centimeters to meter range. And microwaves generally, they aren't what we consider ionizing radiation. So ionizing radiation is the stuff that can damage our DNA. So microwaves, they pass right through our body. They can excite water molecules. That's why we use microwaves, microwave oven in your house to heat up food, because food generally has water in it. So that's why microwaves are good at exciting water molecules, defrosting things. But generally speaking, at low powers, the sort of stuff that your microwave oven or like a microwave transmitter is going to use, it's not going to do any damage to your body. It's not considered ionizing radiation. All radiation can be harmful if it has enough energy, but generally speaking, you're not going to receive a bunch of damaging radiation from microwaves. Okay, so normal yearly background dose, about 85% from natural sources. So we all receive about 3,650 a year. So that's going through your life. That's getting x-rays at the dentist once a year. That's all sorts of stuff. CT scan gives you 10,000. So that's a lot. I know my mom is going through chemotherapy right now. She gets a CT scan every 3 months. So in a year, she's going to have 40,000 microsieverts of radiation as a result of CT scans. So standing close to a microwave isn't bad. There's something called the inverse square principle. So the closer you are to a microwave, the more radiation you're going to receive, but generally speaking, the microwave is going to block it all. So if you're standing a meter, or let's go 2 meters away from a microwave, the power that you receive or the amount you receive goes down by 1 over 2 squared, so it goes down by 4. So you're standing 4 meters away, the strength that you're receiving goes down by 16. If you're standing 5 meters away, the strength you receive goes down by 25. So it's inverse square principle. So if you're standing right next to the microwave, yeah, you might receive a little bit of microwave radiation, which isn't going to do you a lot of harm. But as soon as you step away from it, the actual amount you're receiving goes down really quickly. All right. Let's get to some of the scary stuff here. Let's get into smoking. 1.5 packs a day for a year, 36,000 microsieverts, radioactive stuff in cigarettes. Lowest annual dose clearly linked to cancer is 100,000, which is kind of scary. And if you get to 500,000 microsieverts, decreasing your blood cell count increases your cancer risk to 1 in 250. So this is like the reverse lottery. You buy a lottery ticket, you have a chance of winning, but there's no guarantee. If you receive large amounts of radiation, there's a chance you're going to get cancer, but no guarantee. You could get exposed to 500,000 microsieverts a year for your entire life and not develop cancer. Or you can get exposed to 1 microsievert and that can cause cancer. It's like winning the lottery, but kind of backwards. You'd lose in life. So, maximum radiation levels recorded at Fukushima. This is per hour. So 400,000 in an hour at the Fukushima plant. That's incredible. That increases your risks of getting cancer. So those are all kind of sort of daily ones that you could, relate to. So if you get 1 million microsieverts, it basically starts killing your blood and you get really sick. So vomiting, things like that. It increases your risk of cancer 1 in 125. And that would have been the amount you received in the tunnels, the water tunnels per hour outside of Fukushima. There you go. 2 million causes severe radiation poisoning, nausea, vomiting. Bad day. Really bad day at 2 million. 3 million microsieverts, your increase of cancer is at 1 in 30. So that's even worse. If you get treated right away at 4 million, you might make it. You go up to 5 million, a single dose. So if you get exposed to 5 million, it would kill 50% of the people that got exposed to it within a month. The rest would probably develop cancer and die in the rest of their lifetime. That's really not good stuff. 6 million. When the Chernobyl reactor melted down in the Ukraine, the people who were there to witness it firsthand got a dose of 6 million, and they all died. We're up to 8 million is fatal, even with treatment. And then down here at the bottom, 50 million microsieverts happened when the reactor at Chernobyl melted down. If you were standing next to it for 10 minutes, you would have received 50 million microsieverts. So this is why they're covering Chernobyl with this huge dome to protect all of the stuff. Was it like a cheesy horror movie, Haley? I know one came out lately. Not lately, like a few years ago. It's a pretty interesting place. This kind of scary, nature's taken over. Yeah, okay. If you play some video games, they have some scenes from Chernobyl. I think one of the Call of Duty games has some scenes from Chernobyl. It was really creepy. I think I watched it too, where they like sneak in the back and then they get stuck, their car breaks down, and there's like crazy bears and stuff chasing them, and yeah. All that realistic horror movie sort of stuff. There you go. So that's kind of radiation that you get exposed to on a somewhat regular basis. All right, I want to go through a few of these questions, and instead of me doing them all, I'm going to get you guys to do a few of them, and then we'll talk about it a little bit. So this again, the whole sheet, there's 2 sheets, kind of like a little quiz. The first half's on half-life, the second half's on nuclear decay equations. So I'm going to get you guys into some breakout rooms in Blackboard, and then each group will have 2 questions to do. You just agree or disagree on the answers. I want you to write the answers down in chat and just explain how you got it. You know, if you're doing like number 5, radiocarbon dating can be used to determine, the following. You know, what answer do you get? How did you arrive at that answer? There you go. So I'm going to move you into breakout rooms if I am smart enough to figure out how to do that. And then we'll go from there. All right. We'll go with that. Anna, Eva, Avery, and Bell's gone. Haley, Savannah, Taylor, go there, and Taylor. There we go. Sorry about that. So you're all in breakout rooms. So if you jump back to Blackboard, you should be able to see in your breakout room, there'll be 2 questions for each one. Is anyone having issues or not kind of understanding what I'm saying? Just minimize that. So you're all in those little rooms, and what you can do is just answer the questions, write down your justification, then agree with the other people in your group or disagree. All right, I'll give you guys all maybe like there's 2 questions there each, so maybe like 5 minutes, and then we'll come back and we'll look at your answers, and we'll discuss them or not. Excellent. All right, so yeah, talk to one another in each of those rooms. 2 questions each, and I'll just kind of jump from room to room and see if I can help you guys out if you're running into problems. But I have a feeling you guys will be okay. All right, good luck. All right, guys. I know some of you have gotten both of them done and some of you have only got one of them done, but that's okay. What I want to do is just make sure we're on the right track, give everyone a chance to look at each of the questions, and then we'll go from there. So I'm just going to jump over to the sheet. And if you're not quite done your questions, that's all right. We'll just go with it. So the first part of the sheet, match the term on the left with the best descriptor on the right. Each descriptor